These are the notes for 3.1, and the topic is really an essential topic for the whole semester of calculus, which is we're going to learn what a derivative is, and we're going to talk about tangent lines and a very interesting concept about tangent lines that we're going to look at. So let's say I've got some function which I'll just call f of x. Okay, I just have some random shape drawn. And let's say that I have a point that I call x, some random input. Wherever x is on my graph of x of f of x, let's go ahead and assume this is a continuous function. It's going to have some output for f of x, and so the ordered pair here would be x comma f of x. And what I'd really like to be able to do is to look at something called a tangent line. I'm just going to kind of jolt your mind back a little bit to back when you took geometry. And when you took geometry, you looked at circles, and one of the things that we discussed was, well, we have some special lines we can draw in relationship to circles. We have a tangent line, which would intersect a circle only once, exactly once. We also have other types of lines, like secant lines. A secant line would intersect a circle twice. We're going to actually be able to talk about tangent lines and secant lines in relationship to functions as well, not just to circles. So if I am interested in a tangent line, here's kind of the central question that I would like to explore. What is the slope or the rate of change? We want to make sure that we are associating slope with rate of change of the tangent line of f of x drawn at x. There are actually going to be an infinite number of tangent lines that I could draw on f of x depending on what input of x I'm using. But there'll be one specific one here, and I'm going to be looking for the slope of that tangent line. So what would a tangent line look like? A tangent line for this little local region right here around this input of x is only going to intercept my line once. So maybe something like this. Now it'll run in, or not my line, my function, it'll run into f of x potentially in other spots, but for this little local portion, it's only going to touch f of x one time. And I want to find the slope of that line. Slope is not that big of an idea. I mean, we are familiar with the idea of how to calculate slope. Here's a formula that we were given in Algebra 1 for slope. This would allow you to find the slope or the rate of change of a line. But this is between 2 points. When I'm looking at a tangent line, well, a tangent line is only going to intersect f of x one time. I really want to be able to find the slope at one point, not the slope between 2 points. If I'm looking at the slope between 2 points, I might be looking at something more like a secant line. Like maybe I choose some other point. So if I look at 2 points, I'm really looking at a secant line, not a tangent line. So I'm going to go ahead and just explore this second point here, which is somewhere else along the x-axis as an input for f of x. I'm just going to say, hey, let's just call this length right here in between these 2 points some random variable h. Some random variable h. Well, then the input for my second point here would be x plus h. The output would be f of x plus h. And I could write the ordered pair here as x comma f of x plus h to represent that second point. And if I'm talking about slope between 2 points, that would be the slope of a secant line, which I'm just going to draw. So this is my secant line right here. I could figure out what that slope is. I really could. But what I want to know is the slope of the tangent line. That's ultimately what I am interested in. And I still don't know how to find the slope of a tangent line. I only have a formula for slope with 2 points. But if I knew the coordinates here for the 2 points on the secant line, I could find the slope of that. And so, in fact, you might notice that the secant line and the tangent line, their slopes aren't totally different from each other. They're kind of closely related. So the question that I have is, how could we perhaps make the secant line slope closer to the tangent line slope? Well, what we could do is we could take the second input here, x plus h, and we could move it closer to the first point, x. Let me see if I can draw this for us. I'm going to go ahead and take this point, x plus h, and I'm going to actually move it. And I'm going to redraw my secant line. And I'm going to move this point. Oops, I guess I shouldn't undo the curve here. Let me get that curve back for f. I'm just going to try to undo this. There we go. I'm going to just take that value of h and shrink it down. And move my input a little bit closer so that h is smaller. Well, my input I could still describe as x plus h. It's going to lead me to some point right here. And my output I could still describe as f of x plus h. And this ordered pair would be x plus h, comma, f of x plus h. And I could still draw a secant line here. But the secant line slope is going to start to get closer to the slope of the tangent line. In fact, what I'd really like to do is to get this point, x plus h, comma, f of x plus h, so close, as close as possible to x. I'd really like it to be really kind of like right on top of x. I'm going to draw it right here and call this x plus h. And then f of x plus h would be like there. So these points are getting closer and closer together. And when I start to draw the secant line, you might see, oh my gosh, this is starting to get closer to the tangent line. And remember, this space in between, this tiny little space in between x and x plus h, we are labeling that distance as h. And now what I'd really love is to make it so that x plus h is actually in the exact same location. Oh, I'm doing some things I shouldn't. So that it's in the exact same location as x. It'd be so cool if f of x plus h was actually right on top of it. If those 2 points could approach each other so closely that h went to 0, boy, then I could make them so close together that when I do my slope formula, I could get a very, very close approximation to the tangent line. What I'm talking about here is talking about this value of h and making this value of h as close to 0 as possible. I'm talking about a limit. What I want to do is I want to take the 2 points, x comma f of x as my first point, and x plus h comma f of x plus h as my second point. And I want to do the slope formula with them, but I would like that distance h between the points to approach 0. This is a limit. I want to do the limit as h approaches 0 of the slope between these 2 points. I'm just going to use the slope formula, which says y2, the second output, minus y1 over y2 minus y1. I'm sorry, x2 over x1. Sorry. Okay, so if I take a look at this can actually simplify a bit on my denominator. And let me shrink up this a little bit. This could simplify to the limit as h approaches 0 of f of x plus h minus f of x over, when I simplify the denominator, h. This limit is going to give us the slope, or the rate of change, at the tangent line of f of x, drawn specifically at some input x. Well, we're actually going to give this slope a specific name. We are going to call that the derivative. When we reference that slope of the tangent line, or that rate of change at an instant for that function, we are going to call that the derivative. And this limit right here is called the limit definition of a derivative. The limit definition of a derivative. We will have other ways to describe derivatives that are actually going to be more convenient than the limit definition. However, the limit definition is our conceptual understanding, so it's incredibly important. There's a couple different forms that you might see this in. Now, I wrote this earlier using h as a variable to describe the distance between the two different inputs. Okay, so again, we want that h, that distance between the two different points, to approach 0.